We were interested in getting a better understanding of the impacts of pine beetle infestation on water quality in local streams and community drinking water supplies across the province. There we go. The goal of our research was to provide a spatial and seasonal assessment of water quality in a range of watersheds with variable levels of pine beetle infestation. We looked at a number of water quality parameters, including nutrients, nitrogen, phosphorus, total organic carbon, a suite of metals, including iron, aluminum, manganese, nickel, copper, and some physical parameters such as conductivity and turbidity. And then we looked to relate these water quality parameters to watershed characteristics such as geology, the forest cover, the road density, to pine beetle infestation, both late and early stage infestation, and runoff processes, the proportion of the watershed that's contributing to saturated overland flow or to shallow subsurface flow. We did this by comparing 15 watersheds across the province over one seasonal cycle. We worked at 3 tributaries to the Quesnel system near Likely, Fish Trap and Jameson Creek near Kamloops, Beak Creek, Trout and Penticton Creek in the Okanagan, Redfish Sitcombe, Anderson and Cottonwood near Nelson, and in the Kimberley-Cranbrook region, Kimberley Creek, Joseph Creek, and Cotton Creek. Looking at some of the spatial differences, so here we've got TOC on the top 2 graphs. This is an example from Fish Trap and Jameson from April through to October. Over here are 4 stations on Cottonwood. We can see peaks during the freshet, as we would expect in total organic carbon. Similarly for Penticton Creek and Anderson Creek, metals peaking in freshet, such as aluminum, although you can see that there's significant differences in the levels, but we say similar seasonal trends with peaks during the freshet. When we look at soluble minerals and salts, such as EC and calcium, we see the opposite trends. We see that dilution effect. So there's Redfish and Sitcombe and Kimberley Creek for EC, and down here calcium in Fish Trap and Jameson, and Redfish and Sitcombe. So there's that dilution effect during the freshet in seasonal in soluble minerals and salts. The variables really correlate out into 2 groups. Here, the soluble minerals and salts, so sodium, magnesium, calcium, EC, and turbidity. And then the less soluble minerals like aluminum, manganese, iron, and TOC. And those 2, of course, are negatively correlated. And those relationships hold through, if we look at data for the watersheds through the entire season, if we look just at freshet, or if we looked at base flow in the summer. This is showing all the watersheds and just a selection of the parameters to get an idea of what those trends look like seasonally. So you can see there's a fair bit of consistency. If we look at aluminum, for example, we get that peak in the freshet. Now there's a few watersheds we've noted here with the asterisks where we have incomplete freshet sampling, so you don't necessarily see that peak in a couple of cases where we don't have good freshet data, or similar with soluble minerals such as calcium, where we see that dilution effect fairly consistently. So here's our group of watersheds, a selection of parameters across the top, and these are relative rankings. So for example, if we look at EC, the low values here are less than 50, the high values above 200. We can start to cluster watersheds into groups, and I'm going to take just the first 5 variables here and use those to cluster the watersheds into groups where we have relatively high levels of TOC, pH, conductivity, calcium, and iron. So that includes Quesnel, Fish Trap, Jameson, and Kimberley. And then the group of watersheds where we have relatively low values, including Anderson, Cottonwood, Penticton, Redfish, Sitcombe, and Joseph Creeks. But if we want to start to explain why we're seeing these spatial differences, we need to look at the characteristics of those watersheds. The physical characteristics, so area, elevation range. The runoff characteristics, so this is the proportion of the watershed contributing to saturated overland flow or to shallow subsurface flow. That's based on modeling work done by Marcus Wheeler's group at UBC and Freiburg, and they use a wetness index, a topographic wetness index, combined with the vertical and horizontal distances to the stream. So we'll look at this in a little bit more detail. We're also interested in geology, so we expect geology will influence stream chemistry. We see there's a group of watersheds that sort of fall out in the granodiorite group. There's a group of watersheds that are dominated by sedimentary, largely silica-dominated geology, and then a group of watersheds that are mixed granite and volcanic basalts. And so we expect there'll be some differences with geology. And we're also interested in land use and land cover. The mountain pine beetle infestation data is based on the forest health database, so the later stage infestation and then the more recent infestation and the proportion of the watersheds affected, and the density of roads was something we also wanted to look at, kilometre of roads per kilometre of watershed, as we expect that to influence turbidity in particular. A bit more detail on the forestry, on the pine beetle database. These are the example maps for the 3 watersheds in the Quesnel Basin. And you can see that they're ranked according to greater than 50% infestation down to less than 1% infestation. So what we did for each unit, for each area base, we looked at what category it fell into for that time period. This example for 99 to 2005. So if a land unit had 30 to 50% infestation, we would attach 40% of that area base as being infested, and that's how we calculated those percentages. So what kind of relationships do we find? Well, a couple of things fall out. First, geology turned out to be very important. This is an example of granites, the granitic watersheds, negatively correlated with calcium, magnesium, pH, EC, and turbidity as we expect. Higher granite, lower turbidity rates, lower soluble salts. So that was one important relationship. We also got relationships with vegetation, particularly total organic carbon, with forest cover and pine cover in particular. And if we look at the runoff characteristics, saturated overland flow and subsurface overland flow, the higher the saturated overland flow dominant in the watershed, we saw lower levels of calcium and EC, higher levels of TOC, and the opposite trends, although not always statistically significant, for subsurface flow. First, starting with the geology, it was really an overriding factor. We look at iron and aluminum here on the top. This is comparing the granodiorite watersheds with the volcanics and the sedimentary watersheds. Higher levels of iron and aluminum in the granodiorite watersheds, lower levels of calcium and EC as we'd expect, those increasing in the sedimentary watersheds. So those 4 indicators, iron, aluminum, calcium, and EC, allowed us to separate out geologic influence in terms of water quality. To look at the other factors, what we need to do is then stratify by geology. So here's an example where we're just looking at the watersheds that have granitic geology as their dominant geology, and then looking at, so there's greater than 20% of the watershed here we're comparing saturated overland flow with subsurface flow. So more than 20% of the watershed is contributing to saturated overland flow versus less than 15. And we see that within these watersheds, magnesium, turbidity, and total organic carbon are higher, so where we've got more saturated overland flow, higher TOC and turbidity, and then the opposite trends show where we have watersheds which have a greater proportion of shallow subsurface flow. Again, looking at, first this is just the overview map for pine beetle, so you can see the overall level of infestation higher in the Quesnel and Kamloops regions in comparison to the Kootenays. Again, looking within just the granitic watersheds, we look at forest cover characteristics. This is the proportion of pine, greater than 50% of the watershed in pine versus less than 20%. Higher pine cover, higher iron, higher turbidity, higher TOC. When we grouped by mountain pine beetle, however, we didn't see these same kind of results. We get relationships with percentage of pine, but we didn't see significant trends with pine beetle. So what's this telling us? First, starting looking at geologic versus vegetative differences. In terms of indicators for geology, calcium, EC, iron, and aluminum allowed us to separate out geology. TOC was a very good indicator for vegetative characteristics, and particularly pine. So those are indicators we want to monitor more and pay more attention to in the long run. Turbidity overall wasn't high in these watersheds. We didn't have sufficient enough range to really show land use impacts, and points to the need for sort of next steps to focus more on event analysis and more continuous monitoring in a few particular watersheds. Geology was an overriding factor. When we stratified by geology, we got relationships with forest cover and with pine and with runoff characteristics. So this suggests to us with time, as we start to see more impact on the hydrological regime, that will translate into impact on terms of water quality. In terms of long-term monitoring, we didn't see good relationships with mountain pine beetle, but the relationship with pine cover suggests that with longer-term monitoring we'll be able to improve that capacity. We had some issues with scale, not unlike Marcus's databases. The land base is very dynamic, and some of these regional databases aren't that up to date. The team has sort of suggested that this next step, in addition to the regional assessment, we do more detailed work in specific watersheds where we can get a better handle on the processes and the interactions between mountain pine beetle and key indicators such as turbidity and TOC. The research results from this study show us that there's really a longer time lag between mountain pine beetle and water quality impacts than what we looked at. And in the short term, the water quality concerns are largely related to management and to harvesting. And that's the website for our project, and the technical report for water quality is there, and my email address if you want more information.
Thank you, Sandra. Yeah.